All right. So there is a quiz on Quarkus. We're getting back into it. So take a look, please. And I'll do it in a minute as well. You don't have to put in your answer in case you don't want to. All right. Yeah, so I think the syllabus promised 12 quizzes, so it's going to be like a quiz every day, more or less, I think, which might be good. So okay, so what have we? Here's what we have been doing, right? So to remind you, this is the problem. So the problem is to come up with the minimum cost painting scheme for the houses. And then the cost, for example, to paint this house red would be 7, right? So the cost array is the costs for the individual houses for particular colors. So for example, cost I red is the cost of painting house number I, like 3 or something red. And then RI is different, right? So RI is the minimal possible cost of painting everything up to house I, including house I, and having house I be red, right? So this is, for example, if you're saying R4, this is saying if I definitely paint house 4 red, what is the minimal cost of making everything from the left and up to house 4 painted? And the additional rule is that you're not allowed to paint adjacent houses the same color. Make sense? So that's the answer. I believe it is C. Hello, Yang Yang. Okay. So that's like that. So what we've done last time on this. So this is where we got last time. So we were basically implementing the scheme, right? So the idea is you compute R1, G1, B1, and then you do R2, G2, B2, and so on, up until you have R6, G6, B6, assuming you start with 1. And then once you have R6, G6, B6, you can figure out what the actual minimal cost is, because it's just the smaller one of R6, B6, and G6. Are you with me so far? Are there questions? Who's not with me? Why? Okay, seeing no objections. So, okay, so this is the code from last time. It's also linked from the slides, right? So what are we doing here? So this is just the array that has the costs for painting. Okay. The cost for painting in red, blue, and green. All right. It's a little bit distracting, so. Oh, okay. Okay, now I got to find out what the other people look like. Okay, all right. So what we then do is we set up the cost array. So the cost array is R and G and B. Is it like a new Zoom thing that you can do now or something? Okay. How do you do that? Okay, I'll find out for next time. Okay. So, so okay, I'll try not to be distracted. Okay, so the cost array is just all zeros initially, right? So this is like R0, G0, B0, R1, G1, B1, and so on. Yeah. The slides are linked here. So slide 103. Okay. So, all right. So this is this. And then we just compute R, G, and B by first computing, for I equals 0, I equals 1, I equals 2, and so on. Just because in Python, it's easier to do it with zero-based indexing, and in math, it's easier to do it with 1. So how do we do that? So we start by saying, okay, so cost. So here, this is just kind of easier to type out, but this is the same as, to be clear, the same as this, right? And then we just fill in the first column, the second column, the third column, and so on. So the first column is just 7, 3, 16. And that is what's happening here, right? Why is it, anyone, that the first column is just 7, 3, 16? Anyone? Yeah. Yeah. Yeah, exactly. So what is the RGB thing? It's the cost of painting everything up to house I. If you're only painting the first house, then the cost of painting everything up to the first house is the same as just the cost of painting that house. There's nothing to the left of it. Right? So for that reason, the cost initially is just 7,360. Right? So then we move on to the next one. So what we got to do is we got to compute the cost now for I equals 1, right? So we filled out the 0th column, and now we're moving on to column number 1. So what's the total cost of painting this guy red? Well, it's 6 plus the smaller one of the cost of green and everything to the left, or the cost of blue and everything to the left. Make sense? So here it's a little bit misleading because those are the costs, not the total costs. So when we're going to be computing R3, G3, B3, we've got to look at R2, G2, B2 and use those equations. So you can't read off R2, G2, B2 from here. Those are the costs, not the RGB thing. Make sense? And that's what's in the code, right? So we're saying for column I, just look at the direct cost of painting the house this color, so color 0. And then either you pick either you pick the color for either you pick color number 1 or you pick color number 2 if here this one is 0. And then since this one is 1, you're minimizing between 0 and 2. And since this one is 2, you're minimizing between 0 and 1. Make sense? And as someone last time observed, you could do it recursively, and we will do it recursively as well. But for now, let's just do it iteratively. It's really the same thing. It's almost a matter of just changing the square brackets to round brackets. Right? Because here, like in math, you usually write with round brackets. You could think of those things as functions. You can think of those things as arrays, as long as the values for input smaller than I have been computed. It's the same as accessing an array. Does that make sense? So, okay. So now what we want to do is we want to first just get the min cost of everything. So this would be the minimal cost to paint 06 houses. So this is saying, well, I don't know whether I'm going to paint the last house with color 0 or color 1 or color 2. Whichever one's the cheapest, that's the one that's in the actual solution. Make sense? So that gives us so we know what color to paint the last house, whichever one corresponds to the smaller one of the costs. And we also know the total cost. So given that, we can actually work backwards and say, okay, what color should we paint house number 5, right? So how do we do that? Well, if I know that this one is green, let's say that I know that house 6 is green, and I know what my cost is, I can, for one, just check whether 8 plus the cost up to here or 8 plus the cost up to here is the cost that I'm actually looking for, or just which one is the smaller one, and just pick that. Right? So so to reiterate, if I know already that I'm picking this one for this or that reason, then I'm going to say, okay, so I know that I'm picking this one, and I know the costs. If I paint house 5 blue, if I paint house white green, if I paint house 5 blue, I know the costs. I can just pick the smallest one. That's not constraining me in any way, right? Because that is actually picking the house that will be the cheapest, the paint job that will be the cheapest in the long run. That's in contrast to going from the left, where I couldn't have just said, well, just pick the cheapest one, because if I pick the cheapest one here, it might be that down the road I find out, oh, that did not work out for me. Does that make sense? So we kind of did an example last time, but is anyone not okay with this? So, okay. So let's look at let's look at the code. So what we're doing basically is just picking the colors for all the houses. So I start with just a bunch of zeros, and I want to fill it in with, colors 0, 1, 2. So what I do is I say, okay, so I'm picking the color for house n-1. How do I pick the color for house n-1? The smallest of those costs. And that's what's happening, right? So I'm saying if this is smaller than the other one, pick this one. If this is smaller than the other ones, pick this one. Otherwise, the color is 2. Is that all right? So that's the last house. So now we just go backwards. So we go from I being n-2, and we go down. And now I'm just going to say, okay, so try every color. So 0, 1, 2. If I already picked the house on the right to be that color, that doesn't work for me. So can't pick that for house I, right? And then I'm just going to say, okay, like if uh, if you see a cost that's smaller than what you've seen up to now and the color is legal, then consider it. And eventually it's just going to be, the current minimum color. Okay. Is that making sense? So I'm going column by column. I have my RGB, and I'm just saying pick the one with the smallest of RGB. Here, pick the one with the smallest RGB that doesn't conflict with what I've already decided about house 6. Pick the one that doesn't conflict with that's the cheapest and that doesn't conflict with house 5, and so on. The reason this works mathematically, where going from left to right doesn't work mathematically, is that R, G, and B are the total costs, right? So when I'm saying this is green, I need to know whether this is red or blue. I know what the cost is to paint everything up to this one and also paint this one blue. I know what the cost is to paint everything up to this one and this was red, and paint this one blue. Does that make sense? So I'm storing information here in RGB that's kind of summarizing everything that's been going on up to that point. Make sense? So, okay. So this would be that, and colors. So COLs will now have the right. Questions about this? Yeah. What is the purpose of current min? So, like, there's like various ways of going about it. So basically, I have 3 candidate colors. One doesn't apply, and then I need to pick one between the two. So this is just like assuming that you can have a cost that you'll never achieve. This is like the shortest way to write this code. So I'm just like looking. So this is like this is kind of like similar to like if you want. So I'll just quickly. So like if you want like the location of the minimum in the list, right? You would do it like this, right? So min I is equivalent to Kerman color to Kerman color. Yeah. Wait, this is not min I. Oh yeah, it is. Yeah. So here I don't really do Kerman. I just do like Alet min I instead. Let me do it in a way that's equivalent. So it's kind of like this. So the reason I don't do it like this is because I don't want to be stuck in a situation where actually the 0th color was not allowed. So I can't do it like this, even though it's kind of more elegant. So there's like other more elegant solutions that are like harder to read. Yeah. Does that make sense to everyone? All right. Sorry, can you speak up, or were you not speaking to me? Why do I care? Well, so what I'm doing here, right? So let me do a concrete example. So the question was, why do I care about the minimum? So let me just output the So I just ran every. Oh, it's not happy. Yeah, so I didn't actually change my key bindings. Shift enter. Okay. So if I look at the cost, looks like this, right? So, okay, they're going away, guys. Let me just print the costs line by line. So the costs look like this, right? So this is just the cost. So this is like R, and G, and B. Okay. So now what I'm saying is, okay, I know what the last color is going to be. The last color is going to be 1 because that's the cheapest total cost. So now I need to decide whether house 5 or the house at index I equals 4, if you start from 0, is going to be color 0 or is it going to be color 1? And the answer is it should be, color 0 or color 2, because it's not allowed to be color 1. And the answer is it's better to make it be color 2 because that's cheaper, right? And it makes sense. Like if you look at the costs here, so the 34 you get by 26, the total cost up to this guy plus 8, right? So what I'm doing in this piece of code essentially, this one, is I'm saying go through this guy and this guy and this guy. If this happens to be the index that's not allowed because I already picked this guy, then skip. Otherwise, just find whether this one is smaller or that one is smaller. So by the end of running this piece of code, what's going to happen is per_min is going to be the location of the smaller entry in this column. So this would be 26. And Kerman color is going to be 2, so the actual location. Does that answer your question? Cool. Okay. So this, by the way, was shift enter. I will post a guide to changing the key bindings so that they're like piezo, because that's also what I used. I just did not change it. Just did not change it on my travel computer. Okay. So here's the same thing, except implemented recursively. So what we're doing over here is we're computing, cost 0i as this guy, and we're computing cost 1i as this guy, and we're computing cost 2i as this guy. And all that we need to do is literally just take this and change the change the calls here to actually function calls instead of looking up the solutions that we already built into the lists. So here is what that code can look like. So we can say, okay, so we try. So for every color, we're saying, okay, so what's the cost of painting this color with color I? Well, it's paint house cost at color at I minus 1 plus the current color, right? So it's basically the same thing. Right. So we look at what's the cost. What's the cost if you try, for example, if we're looking at color 1, so we try the cost for the previous one at color 0 and color 2. And then we add the current cost of painting, the house I, this color, which is just the original data, plus the minimum of 2 coals to this guy. Does that make sense? So what we did here was the same thing. So I just did not write it out as a loop. You could also do it as a loop with, for j in 0 up to 2. And you just do this formula. So it's the current cost, so like houses color I, plus the smaller of the costs at I-1 for colors that are not the same as the current candidate color. Right. So same thing. We find, so just kind of like a slightly different style. So we're saying, what's the cost for the color we're considering if we're allowed to consider it? This is the cost of painting so this is like that. And then Kerman, the smaller of the total costs up to I-1 with the 2 colors that are allowed. And Kerman color, which we don't actually use, is the color that gives the smaller total cost. Okay. So if we think about it in terms of base cases and stuff like that, this would be the base case. So we're saying, what is the minimal cost, assuming you paint house I in this color? So if I is 0, then we know the total cost. It's just literally the cost of just painting that one house. Right? Otherwise, we need to try paint house cost with the other colors up to I-1, see which one is smaller, and add the current cost as well. Is that making sense to people? Is that not making sense to someone, and that someone wants to hear another explanation? So, okay. So this is, again, basically the same, right? Why is it possible that this is the same, even though sometimes we had issues with recursion not working out like right away? Well, that's because here we always call I-1, right? So even though it looks like it's recursive, really basically all that's going on is we are, in order to get the answer for I, we need the answer for I-1. In order to get the answer for I-1, we need the answer for I-2, and so on. So we can go from that direction. Or we can just say, well, I'll just write down the answer for 0, and then I'll write down the answer for 1, and I'll write down the answer for 2, and eventually I'll have the answer for n-1 as well. Let me give you an analogy. And this is an analogy that we already had, right? So this is the fib. So I can say, well, just return fib n-1 plus fib n-2. Or I can say, well, I'll just compute the return values of fib from 0 to 1 to 2 to 3 to 4 and so on up until the point where I get the answer to L. Does that connection make sense to people? So, okay. So one last thing. So here the recursive function actually gives us a good way of getting the solution right away. In fact, I kind of embedded the solution here, right? So here I've returned this guy. So this is just the total cost, but I actually know what the color is that I'm using in order to achieve the minimal cost solution, right? I'm just not recording it. So I could record it, right? So I could say, okay, all right. So if I'm returning this, basically, does that make sense? So here, like if I'm returning this value, then that just implies that I think that you should use cur_min as the cost. So that means that you should be using this, right? That's amazing. I'm also getting a call. Okay. So, sorry, can you turn it up? Oh, is it like a lost phone or something? Oh, I see. Okay. Okay, that's kind of annoying. Okay. Did you find it? Okay, cool. So okay, all right. So what do I want to do here? I want to basically record this fact so that I don't have to compute it later on, right? So how could I record this? Well, one way I could do it is I could just record everything that I'm thinking, right? So I could record this fact in, for example, a dictionary. So that would be kind of the most hacky, straightforward thing I could do, right? So here I'm saying, okay, I'm setting up my dictionary. So I want to be able to say, solution solution house I color is what to paint house I minus one if house I is painted color, right? So, okay. I'll initialize it. So I have my N. And here for now, I'll just set it to might as well. So for now, we don't know, but we'll set it up later. Over here, I know the solution, so I can just before I'm returning, this is just a global variable. I set it out. I'll set it outside the function. I'll just say that the solution is like this. Once I have the solution, I can just say, okay, so all we need is the last color, and we can just read off the actual solution from this array. Does that make sense? So if I know that if I know the answer for I minus one, assuming that I know the answer for I can just read it off. All right. So I want to come back to this next time after I introduced another problem, just because I feel like getting kind of the elegant solution would be better. But are there questions about this? Like, do you think you could get the solution if you have SOL here? Questions? Okay, moving on. So, all right. I want another problem. And I think I'll just introduce it. We probably do not have the time to solve it completely. So here's the problem. So we basically want to say we have those denominations. So we used to have a penny, and we have, we have 5 cents, 10 cents, 25 cents, 100 cents, 200 cents, $2, right? And what we want to do is we want to be able to represent any amount using those kinds of denominations, which could be different, using the least amount of coins. So if you're using current Canadian money, then this is not a difficult problem, right? So if you want to say that you need to make like so this amount of money, what's the smallest amount of coins that you can use in order to make up this amount of money? It's 2, right? It's like $2 plus 25 cents. I haven't checked the news today, so like it might be that none of this exists. But anyway, so it's like this, and what's the algorithm for doing it? So like, how do you figure out like what's the least amount of coins that you can use? Yeah. Yes. Yeah. And what happens then? Yeah. Yeah. So you take the largest possible denomination that you have, right? So if you have if you're trying to make 225, then if you have a 2, you should use the 2. There is not a situation where that would not be the situation. Now, it didn't used to be the case, right? So for denominations that look kind of weird like this, let's say that you're trying to make up 8 cents here. The best way to make up 8 cents is to take 2 fourths. So that's 2 coins. But if you use the greedy algorithm and take the largest possible denomination, then you're stuck with a 5, and then you have to make up the rest with 3 pennies. So that's worse. Right? So the greedy algorithm works for this kind of thing. It does not necessarily work for any kind of denominations. And like, historically, so around here, like they had like, the Spanish dollar circulating together with like British coins and stuff, and the exchange rates were weird. So it was a real problem. If you think about pirates, they had like doubloons and stuff. So also like weird exchange rates. Okay. So that's the problem. So formally, the problem is make sense. So okay. So again, like the slide says, so the greedy algorithm, which is something like this, and then take as many of the largest denomination coins and so on. So that can work. There is like actually a somewhat complicated property. So it's not as if they're all multiples of each other, but there is a property that's something like that guarantees that the greedy algorithm would always work. But like we saw in the slide, there are sets of denominations where this just doesn't work. All right. However, you can solve it with dynamic programming in the kind of same style as the houses. So what can you do? The way you can reason is like this. Let's say that this is what I'm trying to do. So I have choices here, right? So I can say either I use 1 cent or not, and either I use 4 cents or not, and either I use 5 cents or not, and either I use 10 cents or not. And if I do, need to make up 7. And if I do, I need to make up 4. And if I do, I need to make up 3. And if I do, need to make up, well, actually, that would not work. So 1, 4, 5. Right? So, okay. So what is the total amount of coins that I use if I make the choice of using 1 penny? The answer is 1 plus whatever I need to make up 7. If I do that, the total amount of coins rather is 1 plus whatever amount I need in order to make up 4. And so on, right? And this is 1 plus min cost 4. And this is 1 plus min cost 3. And here you can do it by I, right? So it's the same reasoning that I used before. The minimal cost of making up 4 is 1 coin because there is a 4-cent coin. The minimal cost, say again? Since I said that there are. Right, since line 13. Okay. Also, there was an executive order, don't ask. Okay. Anyway, all right, so that's the idea. And what this means is that I'm out of time, but what I can do is I can just say min cost of t is the minimum over all of those things, right? So it's the minimum over, do I subtract d1 from t or do I subtract d2 from t and so on. We'll do that on Monday. I will see you then. Bye.
Thank you, sir.
I don't know you, bro.